So, good evening, everyone. I'm Calvin Joseph, and I'm a PhD research scholar at IIT Kharagpur. And I'll be conducting this problem solving and doubt clearing session for this course, controlling total networks and switch mode power converters, which was taught by Professor Sanjay Patel. Okay, he's also from IIT Kharagpur. So, today we'll be discussing the following. So, we will consider an introduction to DC-DC converters, then voltage regulators. Also, we'll talk about the mathematical modeling to design, solve questions, and then also, if time permits, we'll have MATLAB demonstration also will be done. Okay. So we will start with the various DC to DC converters. So can you guys tell me which DC-DC converter is for step down? Which is a popular step down converter which you guys know about, which sir has also taught? Okay, yes. So as Vishal said, it is the buck converter. Okay, it is the buck converter. So this is for step down. And can you tell me what is the voltage gain expression, that how do you know the expression between output and input voltages? That is whereby the output is what into Vn. Okay, yes, correct. So the output is equal to V into Vn. Okay, similarly, we have a boost converter. Which is for step up, and that output expression is given by what?
V naught is equal to Vi by 1 minus D.
Yes, Vn upon 1 minus V. Okay. Similarly, if you have the buck boost converter with the two switch configuration one, then what would be the expression? Hmm? So the output voltage is of a reverse polarity than the input voltage. But in a buck boost converter, we can either step up the voltage or step down the voltage. Okay. So what is the formula? What is the conversion ratio formula?
D into V in divided by 1 minus D.
Yes. So it is D into V in divided by 1 minus D, but you will have a minus sign. Okay, there'll be a minus sign which will be there. P. So till here, are there any queries? Okay. So let us consider the simple buck converter. Okay. So we will have your input voltage being given over here. So this is your gate signal Q. Q bar is the complementary one, followed by your inductor, capacitor, and this is your load, R. Okay. So this is your buck converter. So this is the current IL. This is the voltage V output. So we are considering, let us say, an ideal buck converter. We are not considering, the resistors in the switches or the resistor in the inductor or the ESR over capacitor. We are not considering. We are just considering ideal buck converter. So what happens in a buck converter is, let us say, this point, okay, this node, that is your node Vx. Okay, this node Vx is actually known as your switch node voltage. So what happens is we give a gate signal Q, okay, which will be like this. Some gate signal like this, etc. Okay, so this is your gate signal, and Q bar will be a complementary signal with some dead time. Those are some advanced stuff. Okay, so how will your IL current look like? IL current will fall and then it will rise. It will rise over here, it will fall again over here, again it will rise. Okay, and again it will fall. So this is your IL current. Similarly, you will have an output voltage. Okay, in the case of a buck converter, when your IL is increasing, okay, we will have this average value. The average value of your buck converter, this inductor current, this is actually your load current, I output. Okay, so this is your load current, I output. So when your inductor current is less than your output current, then what will happen is, your voltage will fall. Your voltage will fall. And once it becomes higher than your load current, then your voltage will rise. Similarly, again, it will fall and rise. Okay, so this is the way the output voltage will look like. So this is how you have your inductor current and your output voltage for a buck converter. So how do we get this expression V output is equal to D into Vn? We will do something which is known as the volt-second balance of the inductor. So we have this voltage VL, okay? So when your switch Q is on, that is when Q is equal to 1, your VL is actually equal to Vin minus V output. But when your Q is equal to 0, your VL is actually equal to minus V output. So what do we do in volt-second balance is, we will multiply it with the duty, how much time it is on or off. So it is D T into V in minus V output plus 1 minus D T into minus V output. This is equal to 0. So this T and T get cancelled. So it becomes dV in minus dV0 plus 1 minus D into minus V0. This is equal to 0. So this becomes equal to, so your dV in minus V0 is equal to 0. That is why your V output turns out to be equal to D into V in. Okay. Any doubts in this part? Okay, I hope this part is clear. So this is for the buck converter. Similarly, we have our boost converter. Okay, so actually the boost converter is used for step up and its configuration is given like this. So you have your input voltage, then you have your inductor, then you have one switch like this, which is the main gate signal. Then you have your complementary switch followed by a capacitor and a resistor. Okay. So boost converter is required when we want to increase the output voltage, which is this is the output voltage, right? And it is used many places where we want the input current to be continuous. You want the input current is continuous. While in the case of you see a buck converter, this I input current actually is discontinuous. Let me draw it one over this space. Let me just try. Sorry. This part, your input current will actually be like this. Your input current will be like this, come like this, draw like this. So this is actually your input current for a buck converter. So in a buck converter, the input current is discontinuous. Okay, so the effect of that is different. So buck converter is preferred where you want your this current, inductor current, is close to your output current. So your inductor current is kind of continuous. So you want a continuous current, so you use a buck converter. When you want a continuous current at the output. But if you want a continuous current at the input over here, then you will use a boost converter. Okay. Similarly, let me draw some operating waveforms for a boost converter. I think I should make it like this so that it is visible. Let us say this is my gate signal Q. Okay. This is Q. Your inductor current will look like this. Will go like this, fall, go like this, fall, again rise. So it is like a periodic waveform. It will have a rise, fall, rise, fall. Your output voltage, in the case of a boost converter, okay, over here, your output voltage will fall. Okay, and in this case, it will rise. Then it will fall, and then it will rise. And again fall. Okay, so in the case of a boost converter, the output voltage pattern is different. In the case of a buck converter, the output voltage pattern is again different. Okay, so they have different reasons for that because of the circuit configuration. Okay, so any queries till this point? Like if you have any doubts, you can stop me. If I'm not audible also, you can stop me. If there are any issues also, you can stop me in between. Okay, you guys have understood very well. Okay. So similarly, there's a buck boost converter also. I'm not going into the details of it much. Next is there is what we have is series voltage regulator. So the series voltage regulator circuit which sir has drawn is you have some input voltage like this. You have some resistance in series. You have your load resistance over here. Okay. So this is your current which is actually flowing. And you want to maintain some voltage over here, the output you want to maintain. Okay. So what we try to do is if your load will change, the voltage also will change. So then we will vary the series resistance. So the series resistance is adjusted in such a manner that this output voltage will be fixed. So this is the concept of a series voltage regulator. But a disadvantage with the series voltage regulator is there's this resistance is there in the path. It will draw lots of current. Like there'll be a current drop to it, voltage drop to it, and that will result in losses happening in the circuit. Okay, so that's why series voltage regulator, they have some small applications are there, but they are not always used. Okay. Next, we have what is known as a LDO. LDO is linear dropout regulator. Okay. So what does an LDO do is it will have, if you see, actually in our lab we use LDOs. So we have what is known as a chip. It is like the chip will be here. This will be the ground pad. This will be the input pad. This will be the output pad. Okay. One which I have used is we will give a 5-volt input over here and we will get a 3.3-volt output over here. Okay. And so there are limitations with this. One is it can only be used for step down. It can be only used for step down. Huh? Also, they have what is known as a dropout voltage. Like a dropout voltage. That is, this V in should be greater than my V out, which I want, plus my dropout voltage. Okay. So if my V out, I want it to be 3.3 volt and my dropout voltage is 0.5 volt, then my V in should be greater than 3.8 volt. That is known as the dropout voltage. Okay. So LDOs also have certain applications. They are also quite popular and used. So where do we use an LDO? It will consume low power. In low power cases, we use an LDO. Another advantage of the LDO is it doesn't have no switching noise. It doesn't have switching noise. This is a bit of an advanced thing, but what happens in an LDO is it is smoothly changing the voltage. It's smoothly regulating the voltage. But if you will see in the case of a boost converter, let us say your output voltage is changing, rising, falling, rising, falling, rising, falling. And it is happening in this time frame T. Okay. So there it is a periodic signal. Further, there are the switches turning on, turning off, turning on, turning off. So that actually generates noise. Okay, that noise is in some applications it is not desirable. So in those cases we use an LDO. Okay, we use an LDO. But you must also be very careful with the LDO which you will use, because like the issues which I have faced is that LDO gets heated up. It gets heated up. So it should have what we say a thermal pad for cooling. That should be there. Okay, it should have a thermal pad for cooling. And I don't know about you guys, but how many of you are working on PCBs and everything? So you will have a PCB. Let us say this is the PCB, and is it not seen? Okay. Let us say that this is the PCB, and this is the LDO which is placed. So this is the LDO which is there, and between the, I mean, okay, this is the LDO which is placed. So between this top of the LDO and the bottom, okay, that at the bottom of the LDO, there'll be what is known as a thermal pad. And there we will keep holes. We will keep some holes in the PCB. So that means the heat, which is, sorry, I think it is blurring it. So the heat which is generated on the top of the PCB will go down via those holes and will get cooled. Okay, so that is one method which is used for cooling the PCB, which is using an LDO or any other sort of these surface mounted components. Yeah. All right. So any questions still here? Any doubts?
No, sir.
Okay. Okay, then we can start with solving the questions. We'll start with solving some questions. We start question 1. Okay, I forgot to mention about shunt voltage regulator. Yeah, sorry. So we have what is known as a shunt voltage regulator. So can you give an example in your labs of a shunt voltage regulator which you have used? Do you guys remember an example? Okay, please make it interactive. Okay.
Then Zener voltage regulator.
Yeah, we have a Zener voltage regulator. Okay. And Zener voltage regulator, like this used a lot. It is used a lot in circuits. So how it functions is it functions like a kind of like a clamp, works as a clamping mechanism. Okay, so you have your Zener diode here. and here you have your load, which is drawing some current. Okay. Let us say you have some input over here, and you have some resistance over here. Okay. So now there is some current I flowing, there's some load current flowing, there's some Zener current flowing. Okay. So now what it does is the extra current will flow to the Zener diode. And it will have some voltage. Let us say it is like some 6.1 volt or something, it is there. It will maintain that voltage of around 6.1 volt. But there are certain minimum and maximum currents which are all required for that. But its job is to maintain that voltage at 6.1 volt. So in case the voltage over here at this point, if it exceeds that voltage, what the Zener diode does is it will conduct lots of current and it will clamp the voltage at 6.1 volt. So this is very useful in clamping circuits. Like if you consider in the sense like in your system, in your power system or in your electrical network, there are certain cases that there will be some noise. Some noise might come, the voltage might fluctuate, the voltage can increase, all those can happen. So what happens is that noise which was in one part of the circuit will propagate to the another part. Okay. So that is first of all not desirable. If there's isolation, it won't propagate, but if the isolation is not there, it can propagate. So what is done is the Zener diode is there. So the fluctuations it will filter out. Okay, it will act as a protection. So in case by chance, by some case, the voltage goes high, it will clamp that voltage. And then whatever is this, let us say this, this is your load. Okay. This load will have some tolerances that it cannot withstand 7 volt. Assume it cannot withstand 7 volt. Okay, so then what will happen? It will clamp that voltage to 6.1. So this load will not be exposed to 7 volt. Okay, so that's how it kind of protects the loads and sensitive equipments. And why are we studying voltage regulators like so much? Like it is being used everywhere, almost in most places. And they are required to give, a regulated voltage. It should give a regulated voltage in spite of, this I naught can vary. Okay, this also input voltage also can vary. In spite of all these situations, all these disturbances, all these non-idealities, still you want to maintain a regulated voltage. So that is why you use these voltage regulators. And nowadays, the equipments which are being manufactured, everything, they are becoming more and more sensitive. Okay, so they have less tolerances for fluctuations in the supply voltage. So that's why we need more better regulators, etc. Okay. Also, I'd like to say that this Zoom meeting will end in like say 8 minutes. Okay, then I will again restart this Zoom meeting because I don't have the paid subscription. So we have a 40-minute limit. So once this meeting ends, I will again restart the same meeting. So you have to join in the same link. All right? Okay. So let us go to the question. Okay. So I hope this is visible because full screen, everything, it is a patent issue. So can anyone tell what is the answer for this question?
Option A.
Option A. What about others? Others are being very shy and quiet. Hmm?
A only.
Hello? Okay. Okay, A. Okay, so option A it is because it provides an other current path. there's another current path I said drawn in the previous diagram. Similarly, it does not have higher efficiency than the series voltage regulator. It has a lower efficiency. And this series voltage regulator as well as the shunt voltage regulator, they cannot be used for step-up operation. Okay, so this is a very easy question. And in your NPTEL exam, you usually will have two types of questions. One is where you have options. Like it's an MCQ. One type of question is like an MCQ question. Okay, where you will be given 4 options and you have to select one of the options is correct. Similarly, you can have questions that are numeric answer type questions, where you are told to solve a sum. They tell you find what is the duty ratio required for this converter, something, they give a question. Then you will do the calculations and you have to remember that cannot take your actual calculator. You'll have to use the gate type online calculator for the exam. So that you will have to practice with that as well. And you'll have to get the answers. Let us say your duty comes out to be 0.6125, right? There are 4 decimals. After the decimal, there are 4 digits are there. But they will say to give the answer in 2 digits after the decimal that they provide. So you must write 0.61. And you should not worry. Like if you say um, your answer turned out to be 0.6125 and you wrote it as 0.61, it is fine. It will not come like you got a wrong answer or something, because they have a range, they have a tolerance. Okay, they have a tolerance that is from 0.6 to 0.62. Any value in between which you put, it will consider to be correct. That is, the answer is correct. If it goes to 0.63 or 0.6 or 0.6, 0.59 something, then it is incorrect. Okay, they usually have some kind of tolerance. I don't exactly remember how much it is, but there's quite a margin, so you don't need to worry. And for those who will be giving the exams, I'll recommend that you try to solve sums without much on the calculator. Okay, someone was saying something? Okay. So, like I'll suggest that you try to prefer solving sums with minimal use of the calculator. It will be better. Okay, so that the online calculator is a bit tedious to use everything and all that. Okay. So I'll proceed to the next question. So what are true regarding the buck converter? Which of the following are true regarding the buck converter? There are multiple correct answers. So you can tell me which are correct, which are wrong. What have been Omkar, Ankita, Bharat, Arun, Anusri, some guy, Anshuman? Any suggestions? You can tell the answer. It's not that it should be 100% correct, everything. Take a swing.
C is correct.
Okay. Output voltage ripple is dependent on load current. Correct. Then
D is incorrect because voltage across the switch will be V in minus V0.
okay. Okay.
No, sorry. D is also correct. V in voltage across switch will be V in.
Okay.
A is incorrect because we can operate it in no load.
Okay. Correct. Correct. Then
B, I didn't understand what is the meaning. Direct energy transfer means?
Okay. So direct energy transfer, let me draw. Okay. So let me go to a new page. Let us go over here. So when your gate signal is on, that is your inductor current is rising, that time also it is feeding power to your load. It is transferring that energy to the output. Then when your gate signal is goes down and goes off, that time your inductor current is falling, right? And that time your output is discharging, right? So directly when you're turning on the main switch, the energy is being directly transferred. That is why it is known as a direct energy transfer converter. But in the case of a boost converter is opposite. When you turn on the main switch, your inductor will store the energy. And then when you turn off the main switch, then the stored energy in the inductor, then that energy is transferred to the output capacitor. But in the case of buck converter, directly the energy is stored into the inductor and into the output capacitor. One is, let me say, this is my buck converter. Okay. This is your Q. This is your Q bar. This is your L. This is your C. And this is your load R. And this is the load current I naught. Okay. In the case, okay, and further explain buck converter in a better sense, let me, there are two cases. When Q is equal to 1, what do we have? This is your input. It is directly connected over here. It goes to the L, C, and R. Right? This is your IL. This is your IL. This is your V0. Okay? This is your case Q equal to 1. When your Q...
Sir, can you use black color?
Okay. Okay, black color. Okay. Okay. When Q equal to 0, this is my VN. VN is disconnected now from the circuit. Okay. And then this is your L, this is your C, and this is your R. Okay. This is your IL. So your IL actually flows like this. This is how your IL flows. Well, in this case, your IL flows like this. Okay. Now, this is your I output. This is your I out. Okay. So, even if your I naught is 0, your I naught be 0 when your R is infinite. When your resistance is infinite, that means your output current which you are drawing is 0. Okay, so that is known as what is known as that is a no load condition. Okay, this should not be arrow, sorry. That means your R is infinite. That is known as a no load condition. So that is fine for a buck converter, but it is not permitted for a boost converter. It is not recommended. Why in the case of a buck converter is fine is because the inductor current is having a path. It is flowing like this, and then it is discharging like this. There is the inductor current can completely go this, and it will work. There will not be an issue. The issue won't be there. So this is regarding no load. Second question is regarding direct energy transfer is the input voltage energy is directly fed to the output voltage directly. But in the case of a boost converter, initially the energy is stored in the inductor, and when the configuration is changed, then the energy is transferred to the output. Okay, that is why that is required for boosting operation. So that phenomena you will see even in a buck boost converter as well. So in all these boost derived converters, first you have to, for some time, you have to store energy in the inductor, and then you have to transfer the energy to the output. Okay, so that's why it is indirect energy transfer. But in a buck converter, directly the input voltage energy is transferred to the output when you connect it. Okay, that is why it is direct energy transfer. Then what was the other 2 points where output voltage ripple is dependent on the load current and the switch voltage stress is Vn. Okay. So first I'll consider switch voltage stress. If you will see in this case, okay, this is your when Q is 1, when Q is 1, that means what? This switch is connected. Okay. When this switch is connected, this switch is off. So in power electronics, we like the switch is the the switches are really important, right? The switch will turn on, turn off. Okay, it is either on or off. Okay, and when the switch is off, what happens is there'll be some voltage will be there. Some voltage will come, and that is known as the blocking voltage, which is required for the converter. Okay, so when your Q is 1, what is the voltage which has come across this switch? That voltage is your Vn voltage. Okay, that voltage is your Vn voltage. Similarly, in this case, this switch is open, right? So what is the voltage across these 2 points? That also voltage also is Vn. So for the switches of a buck converter, the voltage stress is actually equal to Vn. Any queries in this part of the voltage stress?
Sir, Q is equals to 0. Please, can you repeat it, sir?
Okay. So Q equal to 0 means this is connected. Okay. And this is disconnected. Okay. This is open, this is closed. So your circuit will be in this format. You have your input and you have and this switch is open. This switch is closed. Okay. This switch is closed. So this is ideally connected to your ground. Okay. It is connected to your ground. Let us assume, let us not consider the parasitics, etc. It is connected to the ground. Okay. This is your inductor. This is your output filter capacitor. This is your resistor. So the voltage at this point, let me use a different color. The voltage at this point with respect to ground is Vin. And the voltage at this point during this mode of operation when Q equal to 0, this is 0 volt. Okay. So the effective voltage which is coming across this switch, that is Vn minus 0, that is equal to.
Yes, sir.
Okay. So that is, so when you will select for selection of switches, the black poster required for selection of switches, there are many things. Hopefully you guys will all in your projects or in your actual work which you guys are doing, you'll be using all these things. So you have to select the switch which will be able to withstand this input voltage, and we usually consider a factor of safety. So let us say if the actual input voltage is, let us say 48 volt, we will use a 100 volt switch. Okay, double the voltage, etc. Because what happens is during switching there are certain transients, so we have a factor of safety. That you would have learned in design, you should keep a factor of safety. Secondly, you will see how much is the current rating of the switch, like how much current can it flow through that switch. Okay. Another factor which you will look into is like the on resistance of the switch. Like the on resistance is less, then there'll be less loss. When there's less loss, then you are happy, efficiency is more. Similarly, cooling requirements are less, right? Another part is there's something known as a QG, or that is gate charge, which is required to turn on and turn off the switch. Okay, that's why if you guys remember sir had mentioned something known as wide bandgap devices. Okay, wide bandgap devices are good because the on resistance is less, the QG also is less. So like they have very good characteristics as compared to the normal silicon switch. Like silicon switch is being used extensively in power electronics, but now people are slowly switching and adopting all these wide bandgap switches, which are gallium nitride and silicon carbide. Okay, because of their better characteristics, etc. Okay, so that's how you select your switches. There are later parts of this course also. Okay, in this course it's not there. But selection of switches is a important thing. If you want, I can also put a link to any video which says how to select the switches. Okay. Mm. Okay, so that completes the voltage stress. Next is output voltage ripple is dependent on the load current. So this is your IL, this is your output, this is your IC. So your IC.
Sir,
Yes.
if the voltage input voltage is V in, what should be the what should be the rating of the switch?
Yeah, the rating should be higher than beam, maybe like 1.5 times or 2 times that rating.
2 times.
Yeah, even up to 2 times, we think.
Okay, sir.
Yeah, because there are switching happens and there are there are those spikes. Those spikes are there. That is, sorry, the voltage across the switch. Ideally, if you assume this is V in and this is 0, we think it looks like this, but practically there will be these kind of spikes. There will be this behavior. Okay. You might be able to see this behavior. You may not also be able to see this behavior in the oscilloscope because this behavior is very high frequency behavior. So if your oscilloscope bandwidth is low, if your probe bandwidth is low, this behavior will not be seen. Okay, but it is actually there. It is actually there in the circuit. So if this is Vn, this might actually be 1.5 times Vn. Okay, so when such things happen, your reliability of your switch will go down because it is withstanding very high voltage. It's not rated for that. Okay, so because of all these considerations, we take a factor of safety. Okay, this is one of the reasons. Okay, next part is why the voltage ripple is dependent on the load current. Now, why is it dependent on this? Okay, because your capacitor current is equal to IL minus I naught. Okay, IL minus I naught is the capacitor current. So, and what is your voltage? This is your C dV naught by dt. That is equal to IC. So your V naught is 1 by C integration of IC into dt. So what we can know is this, and this actually is your ripple voltage. This is the ripple voltage of your buck converter. Okay. So this is your ripple. Or we V output ripple. Let me just say ripple. Okay. So your V output ripple voltage is directly proportional to your capacitor current. And this capacitor current is directly proportional to your load current. Although the polarity is different, in actual sense, it is proportional to the magnitude of the load current. That is why when your load current will increase, your capacitor, the voltage ripple also will increase. This you can observe. Okay. Any other queries? Okay, I'll proceed to the next question. Then.
Okay. Okay.
So the third question is a very simple one. Like, what are the wide bandgap devices that are gaining popularity in power electronic applications? silicon is the current old or the traditional one, which has been used, very well tested, everything. And they are manufactured it and brought it to as best as possible as they can. And they're still trying to make it better as well. But gallium nitride, that is GaN, and silicon carbide are being adopted in a wide way because they have certain characteristics that enable it to withstand higher voltage stress, which can allow the junction temperature to go quite high as compared to silicon and all these things. Okay, so silicon carbide is preferred for higher voltage applications. Okay, it's preferred for higher voltage applications. And so at those very high voltage applications, yeah, correct. She said the answer is D, correct. And at those very high voltage applications, usually they were IGBT switches which were used, but now they're slowly being replaced by silicon carbide. And gallium nitride, they can, to get very high voltage for gallium nitride is not that popular, but they are more popular for low voltage application like 100 volt, 200 volt, etc. And gallium nitride can switch very fast. The switching frequency is very fast. It's possible to go at that very high switching frequency. And you will learn in the next week and also I will discuss about, ripple. Like how do you have a current has a ripple, your voltage output voltage has a ripple. And this ripple is dependent a lot on your switching frequency. It depends a lot on your inductor and capacitor which you select. Okay. So that's why if you make your switching frequency high, the switching frequency is high, then the amount of inductance, the amount of capacitance which you require is less. When you will derive those expressions for inductance and capacitance, you will see that the switching frequency is in the denominator. Okay, so if you increase the switching frequency, the size of your inductor capacitor will become smaller and you get more and more compact power supply. So if you would have noticed your laptop charger, your phone charger, they're, as you see the days are going, they're becoming smaller, more compact, everything, right? Because you don't want to carry heavy stuff, etc. And that is because, power electronics is going for much higher and higher switching frequencies. Okay, so this is why wide bandgap devices are very popular. Okay. So we'll proceed to the next question. Okay. This is a boost converter. So I have drawn and shown two boost converters. So can you tell what is the difference between both of them? Are they the same or they are different? Sorry.
They are different.
Okay, they are
One is
different.
unidirectional, another is bidirectional.
Okay. Bidirectional in the sense of what?
So the diode is, unidirectional in nature,
Okay.
whereas replacing with a switch helps us to, conduct the current in both directions.
Okay. Great. Yeah, so current is going in both directions. Can go in both directions in the second case. Okay. So the one on the left, that is known as an asynchronous boost converter. Okay. Because your current cannot go negative. Like a diode, once the current tries to go negative, the diode will turn off. Okay. There might be some reverse recovery, all those small phenomena are there. Non-idealities are there. But let us consider from a control system perspective that diode cannot allow current to go in the negative direction. So this is for this case. And in this case, your current can go in both directions. It can go in both directions. So, whether I can edit. I think I can edit over here as well. Yeah. Okay. So, this way. So this is your, it's not the option to edit, sorry. Pen. Okay. We'll come to it later, Arindam. Just hold on. Okay. So here, current can go in this direction also. It can also go in this direction. Both directions it can flow. But in this case, current can only go in this direction. So I think many of you would be familiar with this left side one, where you have your main switch and you have a diode, right? But this configuration also is there. And like, why do you want current to go negative? Like, is it at all desired for you? Is it at all good that the current goes negative? Do you guys think it is good if it goes negative?
To avoid discontinuity.
Okay, avoid discontinuity also is, yeah. So this operates in DCM. If the load is very low, that is current is very low, and this will always operate in CCM, right? So that is one thing. CCM, what happens is, in usually right now, in most cases, we use this synchronous switch. Okay. So anyway, the current will go through the body diode of the switch. But if your gate signal is high, it will also go through the channel of that switch, right? And that channel, that switch has lower on resistance as compared to a normal resistance of a diode. So it is more efficient. That's why we prefer this configuration. Okay. So that is one advantage of it. Secondly, there are certain scenarios where we want to flush out the output voltage charge stored in the output voltage quickly. In that case, we want the current to go in bidirectional operation, so we operate it in the CCM mode. Okay, DCM also is widely used. Like, you can make this converter, which has this switch, also operate in DCM. How do you do that? You always set Q1 bar equal to 0, right? I think sir has shown, right? How do you make a MATLAB model such that you can enable DCM or you can disable DCM, right? If you make this Q1 bar equal to 0 all the time, that is irrespective of whether Q1 is 1 or Q1 is 0, if you make sure that Q1 bar is always set to 0, then it will operate in DCM. It could operate in DCM. Okay. Okay, so sorry, we got diverted from the question. So we are considering this boost converter where we have this load I output. Okay, you have your I output to be equal to 5 ampere. Okay. Then you have your average inductor current, IL. So this is very slow. Slow, but it's better if it's here. So IL, this is equal to 15 ampere. Okay. Now, what is the expression between IL and I output? Can you tell? What is the mathematical expression between IL and I output?
IL into 1 minus D equal to I0.
Yeah. I0, okay. Let's see. So I0 is equal to IL into 1 minus D, right? So what we don't know D, right? So can you calculate and tell me what is D?
Two by 3.
Okay, so D is equal to 2 by 3. Okay, what is the V output voltage? What is V output voltage?
5 volt.
Okay, so the output voltage is actually your load current into the load resistance. So 5 ampere into 1 ohm. That is why your output voltage is, sorry. No. So your output voltage is equal to 5 ohm. Okay. So what is your input voltage then? Is this true? Hello? This is very difficult. I think it's simple, right?
I think it is not correct.
Huh? Because we know for a boost converter, V output is equal to V in upon 1 minus D. Right? This we know. Just take it this side. So you get V in is equal to V output into 1 minus D. Right?
Yes.
Hmm.
Okay.
So then what will be my V in then? Okay. So that is actually equal to 5 into 1
5 to
minus
3.
2 by 3. This is very small. 1 minus 2 by 3 is 1 by 3. 5 by 3 is how much? 1.667. Okay, 1.667 volt. Yeah. Let us
Yeah.
see our Arindam Maulik already got the correct answer. It's very fast. So are there any doubts in this question or can I proceed to the next question? So you asked me, okay, these are hard questions. I admit this is a hard question. Right? It is lengthy, it is little bit tricky. Okay. Like I've twisted it a bit. I have not given the output voltage directly. I've given 5 ampere and load resistance. So from there you have to get your output voltage, right? Then inductor current is 15 ampere. So then you would need to know this expression, right? This expression is important for you to know. Then from there we got duty, and from the duty I got the input voltage. Okay, so one way which will be helpful, useful while studying or while preparing for things, or at least while preparing for sums and exams, everything is you go like you have solved a question, everything. Then after you solve it, you try to recollect what you did, like what are the steps you followed, right? What are the formulas you use? What are the steps, right? So you should have that recap. That recap is very nice, very necessary. So when you have that recap, there are more chances of it sticking in your head for longer duration. Okay, so that recap, I'll try to do a recap at the end of the session, but you should also incorporate recap in your own study sessions as well. Okay. So this is the boost converter question. Let's go to our buck converter question.
One quick question, like
Yes, yes, yes.
initially you mentioned about the charge dump, right? Like, the benefits
Uh-huh.
of having CCM.
Yes,
Can you
yes.
give more insights about it?
Okay. Okay, so I'll have to draw. Let me just I'll keep the annotations 1 minute. So, like this concept in sir is taught in later portions of this course. Okay, but let us say this is your output voltage. We assume the output voltage should be regulated, right? Let us
Mm.
say it was at 5 volt and we took it to 5.5 volt, right? Then we are bringing it back. We want to bring it back to 5 volt. Okay, but this will not happen in this fashion because there's lots of energy storing elements, etc. So this is what curve. This is the desired curve. Okay, or the reference curve. Hmm. But the actual curve, the ripple is there. Ripple will be there. Then it will go like this, and it will go like this. It will be like this. Okay. Then when it steps down, you would want it to go like this and come here. But
Mm.
there could be a case that it will discharge very slowly. Okay, it will
Okay,
discharge very
understood.
slowly. This would happen by because your inductor current, let us say it was over here. When you give a step up after some time, it will rise. Okay, it will rise over here. And then when you give step down, there are two cases. One case is in CCM is it will go negative. Okay, suppose this is your negative portion, 0 ampere, it will go negative. So if it is allowed to go negative, then it would be this case. Okay, but if it is not allowed to go negative, right, then it would reach here, then it would go like this, like this, like this. In that case, the output voltage to discharge, it takes more time. So it takes more time than that. You can simulate and check. Okay. So that's
Mhm.
why it is useful at some places to enable CCM and after some time to disable it. There are many things are there. Hmm.
All right. Okay, I understand now. It's more for like, no load condition where you want to do load regulation properly,
Yes, it is
right?
like more when the load is very
Small.
exactly no load. You can say that it is required when you want to quickly discharge your capacitor. Okay,
Mm-hmm. All right. Yeah. Mm.
if this is your capacitor, this is your load, this is your load, right? This load
Mm-hmm.
is very high. When this load is very
Mm.
high, the capacitor will discharge very slowly. So if you can
Mm.
have a provision that you can send current to this direction as well, then you can
Mm.
discharge the capacitor, right? So
Yes.
that
Yeah.
is why we use this method. Hmm.
Perfect. I understand now. Thank you.
Okay. Next, we'll go to the buck converter. Okay. Okay. So actually, I have made a mistake. So I have written a synchronous buck converter, but actually it is a asynchronous buck converter. So there's a mistake on my part. Okay. Now, yeah, you can access these sessions later. So let me do one thing is, I'm so sorry. Let me share the link. So this is my YouTube channel. So we are required to upload these sessions. Okay, we are required to upload these sessions. So I'll merge these videos and I'll upload it. So you will get access to these sessions. So there are many cases like people have poor network connectivity or they're busy at some time. Okay. So this is a channel where for my YouTube, for my NPTEL courses which I conduct, the doubt clearing sessions, I upload the videos over there. So you can access it. Okay. So we have a buck converter given over here, right? I think I'll just take a snip because writing over here is very tedious. Let me just take a snip of this. So buck converter. Okay. Any question here? Okay, this is the buck converter. What have they given in the question is load current is 20 ampere with the output voltage of 1 volt. And what is the average current through the high side switch when the input voltage is 12 volt and 4.8 volt? Okay, so we have the load current I output. I output is actually equal to 20 ampere. They have told, what is they have told? Output voltage of 1 volt. Okay, so you have your output voltage of 1 volt. And your input voltage are two cases. One is a 12 volt case and one is the 4.8 volt case. Okay, two cases are there. So what have they asked to find out is what is the average current through the high side switch. Okay, you have to find this current. This current's average. You have to find this current's average. Okay, so how will we find this current's average? Any suggestions how to proceed with solving this question?
We can find average inductor current.
Okay,
That will be equal to the output current.
the Anshuman has given a value. Let us check it. Okay, yes, your answer also is okay. Arindam also has told something. Okay, we will check. Let's check. Okay, okay, someone said who was saying that. Someone said that a load current is equal to your average inductor current, right? That is correct. So your average inductor current is equal to your load current in the case of a buck converter. That is equal to 20 amperes. Okay, it is equal to 20 amperes. Now, we are required to find the current through this switch, the average current through this switch. Okay, so let us see how will that, suppose you have your inductor current. This is how your inductor current looks like. Okay, let me make it smaller. So this is my inductor current. Let us say this is my zero axis. This is my inductor current. Okay, this is versus time. Now, this current over here, sorry, excuse me, this current over here is actually your input current. Okay, your input current. So your input current is equal to your inductor current when the switch is on and it's zero when the switch is off. So that is actually given like this. It is like this, like this. Okay, like this, like this, like this, and like this. Okay, so what we have to do, we have to find the average of this. We want to find the average of this. So how do we find it? What dt times of the inductor current? Like input current is on during the dt time, and during this 1 minus dt time, it is off. So we can write average of input current is equal to d into the average of inductor current plus 1 minus d into 0. That is why it is actually d into the average of inductor current. Okay. So what is the d in our case? In this case, what is d?
1/12.
In this case, it is 1 by 12. In this case, it is how much? In the first case, my duty is 1 by 12. In the second case, my duty is equal to 1 by 4.8. Okay. Right. So that means my average current in one case is, let me write it off over here. For the case of 12 volt, the average current is 1 by 12 into 20. And for the 4.8 volt, it is equal to 1 by 4.8 into 20. So can you tell me what are the calculated values? Okay. Arun has got 1.67 and 4.67 ampere. Okay, we can check that. Devash's question is very good. That I have a question here for both CCM and DCM. IL average is equal to I naught, but for using V output equal to dVin, this relation is only valid for CCM. Shouldn't we check first whether the converter is in CCM or not, since it is asynchronous? Yes, you are correct, Devashish. We should have checked it. But the issue here is in the question, the inductance has not been provided. The value of L has not been provided. So the value of L is what will determine whether it goes into your DCM or not, right? And since your I naught is like 20 ampere, it is like sort of like a very high load condition. So it is unlikely that it will go into DCM. Okay. So since that information has not been provided, we can assume that it's operating in CCM. Okay. Okay. Someone had given answers. So Arindam had given 1.67 ampere and 4.167 ampere, which was correct. And Schumann had given 33.3 and 8.3. Okay, I think he's joining. Okay, so any doubts in this, or I can proceed to the next question? If you have any queries, you can ask, right? No need to be shy. You can send on message, or you can stop me and also ask. Everyone has understood very well, it seems. I think. Okay, very good. So I'll proceed to the next question then. So this is regarding mathematical modeling. Okay. We have this circuit given to us. Okay, this circuit is given to us. Now we have to find the mathematical model of this. So how do we do that? Like, what do you suggest is the method we must follow to find the mathematical model for this? Okay, correct. We write with KVL equations we must do. Okay, let me. This is actually, I think next time I should put it in that other part only. Okay, then replace voltage term with differential terms. Okay, let me draw it instead. Um, so we have L, C, R. Okay, and this is my VL. So let us say this current is I, this current is IL, this current is IC. Okay, this current again is I. Same current has to flow, right? So first we apply KVL, as he has suggested. So we'll do VL minus I into R minus this voltage. Okay, let us name this voltage VL. Okay, VL minus I into R minus VL is equal to 0. Now, what is VL? VL is actually equal to your voltage across the inductor, which is equal to L DIL by dt, right? So that is VL. Now, what is I? My I is equal to current through the inductor plus the current through the capacitor. And what is the current through the capacitor? That is C into this dVL by dt. So this current I is actually equal to IL plus C. Okay, what is VL is L DIL by dt. So this becomes plus CL d2IL by dt2. Okay, so it becomes a second order differential equation. Now we will substitute all this over here. We'll substitute all this over here. So we get VL minus IL plus LC d2IL by d2t into R. My VL is L DIL by dt is equal to 0. Okay. So we get VL minus IL into R minus LCR d2IL by dt2 minus L DIL by dt is equal to 0, or LCR d2IL by dt2 plus L DIL by dt plus IL into R is equal to VN. Okay. So what do we do usually in this case is, it is a second order differential. So order of this differential equation is second order. Next is, we preferably make the coefficient of the highest order differential to be unity. So that's why we scale it by LCR. So we make it actually equal to d2IL by dt2 plus 1 upon RC DIL by dt plus IL upon LC is equal to VN upon RLC. Okay. This is the expression. Any doubts in this till now? Okay. Okay. Suresh, like here, please don't write anything here. Okay, so let us proceed. Suresh, please don't do that. I'll have to remove you then. Okay, so we'll proceed further. Hmm. So this expression is there. So what we do is, as sir told, we add what are known as integrators. So this is 1 by S. So over here it is actually d2IL by dt2, right? Over here actually it will be dIL by dt. Then again we add a 1 by S. So this will be IL. Okay. Now this d2IL by dt3, this actually is what? This is scaled by 1 upon RLC, and this is V in. So this is V in upon RLC minus this DIL by dt is 1 upon RC. We subtract. Similarly, over here, we scale it by 1 upon LC into IL. So this is the overall expression. Okay, so this is the overall way we can solve this dynamical equation if you would add it into SIMULINK or something. Okay. Now, in the question, what was asked is to find out what is the, let me see the question. Determine the current to the inductor which you have got and voltage across the resistor VR. Okay, voltage across the resistor is simple. So you have got IL. You have got IL. Now you have to find the current I. So we know current I is equal to IL plus IC. So that is equal to IL and IC is what? C into dVL by dt, which is equal to IL plus LC d2IL by dt2. Okay. So this is your I. And your VR is equal to I into R. So that is R into IL plus RLC into d2IL by dt2. Right? So if this is the expression, then what we do, this d2IL by dt2, we multiply it by what? RLC. And this IL we multiply it by R. And we add them. This will be our V into R, VR. Okay? Any doubts in this? Hmm? Okay, okay. Okay, so, okay, it would be good if you guys could, you know, introduce yourselves and tell, like, why are you taking this course? Like, what are you doing? You're doing your PhD, BTech, MTech, you're working, or your faculty. You could just unmute and just tell, so that at least, what do you expect from this course? What do you hope to learn from it? What are your objectives, etc.? What do you want from these doubt clearing sessions? This feedback would be very good, useful. So you could unmute and you can tell. Okay. Don't feel shy. Okay, we have many people here. We have Anshuman. He has iPhone, everything. You can tell.
Hello, am I audible?
Yes, yes, yes. Tell.
Hi, I'm Devashish Chakraborty.
Okay.
I have done my masters in power electronics and drives from IIT Mandi in the year
Okay.
2024,
Okay.
last year only.
Okay.
After that, I have joined an organization where I work in the domain of LED drivers.
Okay. Okay.
And the purpose of this taking up this course is to just enhance my knowledge when it comes to the converter control.
Yeah, yeah, yeah. Okay, okay. So in IIT
That is the
Mandi,
main focus.
uh,
Yes.
under which professor did you do your project?
Okay. So initially it was Dr. Narsareddy Tumru. So actually after that, in the middle, he actually switched to IIT Bhubaneswar. In the
Okay.
middle of my by the end of my first year of my MTech.
Okay.
After that, I finished my project under the guidance of Dr. Amit Kumar Singh.
Okay. Okay. Actually, Amit Kumar Singh is a lab senior actually.
Oh, acha. Yes, he done his PhD under the
Professor
guidance of Dr.
Sambhaji.
Shantanu Kapur.
Yes. Yes. Yes.
Yes.
Yeah. Okay. Okay. Very good.
So he is my supervisor also.
Okay. 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 Nice. 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 So you are working in which company right now?
Inventronics.
Inventronics. Okay. And you are in Bangalore
Uh-huh.
or?
No, no, no. It's Gurgaon based.
Okay. Nice. 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 Good for you to join. Huh? Yeah. Yeah.
Thank you.
Yes. Yes. Okay. I think people are leaving. They're too scared to unmute and tell. Mhm.
Good evening, sir.
Yes. Yes. Yes.
Sir,
Tell.
actually, I have completed my MTech in Power Electronics and Drive from Peach University in Bhubaneswar in the
Okay.
year 2014.
Okay.
2014. After that, I was working in one uh, guest faculty in one diploma school in Barampur. And there I have taught for 2 to 3 years. After that, I have joined one degree college as
Mhm.
an assistant professor. I have joined there, and I was doing. But now I plan of doing PhD. So I have
Yeah.
joined in Silicon University, which is in Bhubaneswar. And
Okay.
in our coursework, we need 1 to 2 courses. So I have opted these courses under the guidance of my guide, who is Pratap Sir, Dr. Pratap Sir. He has
Mhm.
guided me because my thesis will be. I'm planning to work in that EV and all by implementing the power electronics concept. For that,
Okay. Okay.
this course, I think that it will be enhance my knowledge and it will be better for my project,
Yes. Yes.
my
Exactly.
thesis. And,
Mhm.
yes, sir.
Yeah. Actually, for PV, you need the boost converter for MPPT everything.
Yes, sir. Yes, sir. EV, I need now. I have done little but more, but by referring to other papers I've done. I have not done by my own. So first,
Okay.
I and my guide have decided to uh, do the coursework. After that, only I will get a better knowledge, and I can proceed by innovating any new
Mhm.
concept and new ideas.
Yes. Yes. Yeah. Yeah. That's what PhD is about. Yeah.
Yes.
Okay. Okay. Yeah. Okay. Then Arun.
Good evening, sir. Sir, I am working as a faculty member in TKM Engineering College, Kerala,
Okay. Okay.
Kollam, and I am doing my part-time PhD at NIT Calicut. So for that, this is used as a course for.
Mhm. Okay. Have you joined a course previously? Or some any other course like digital control? Did you join or something?
No, I did a state space control course in the previous semester. So
Oh,
you were
yes,
the
yes, yes, yes,
TA
yes,
in that,
exactly.
that course also.
Because you sounded very familiar. That's right. Okay. And
Ah,
one other Binita or someone was there, no? Another lady also joined from your NIT Calicut, I think. Don't remember. Okay. Then what about Pingima, Prasad Rao, Srisha, Sudesha? You could also give an introduction.
Good evening. This is Prasad Rao.
Okay. Yes, Prasad Rao.
Yeah, I am working in EB in
Okay.
Telangana, state of Telangana as a senior engineer.
Okay.
Just sake of knowledge, I have joined this.
Okay. Okay. Very good. Very good. Yes, sir. Good to have you.
Okay, thank you.
Okay. So you're working on battery chargers, you know? Shisha, you can tell.
Hi, Kelvin. So I am I'm applying for counseling for MTech. Currently,
Okay.
I'm looking for a MTech college in NITs.
Okay.
So I completed BTech B in 2021. Then I work currently 4 years I have worked in IT company. Now I am planning to do a MTech. So
Okay. Okay.
I'm
MTech in
looking
power
for a
electronics.
power electronics, yeah, in a
Okay.
MTech course. So
Mm-hmm.
just I'm looking,
You're
it would be
brushing up
helpful
your
for me.
concepts.
Yeah.
Mm-hmm. Yeah. Yeah. Okay.
Then it will be this recording will be available to us or how?
Yeah. Yeah. It will be available. It may take some time. Like I've shared the link. Did you get the link for the channel? I've
Yeah,
pasted.
yeah, I got
Yeah.
it. YouTube link, yeah, got it.
Yes, yes, YouTube link is there. It will be uploaded by tomorrow. Okay, because it takes some time, everything, to get it all
Oh,
together and upload. But then it will be there. It will be available. Can access it.
okay.
41.4.
Okay, then this will be minus 41.4. The current will lag. Okay. So
Okay. So I get Singamai Ruik is not introducing himself. We'll proceed further. Okay. So have you guys all got access to MATLAB? Have you just checked that?
We have to check it. So
Okay.
far, we have not accessed it.
Okay. No, actually they sent a mail for accessing MATLAB and for learning material. Okay, so you can check that and you can proceed.
Okay.
Because Sir has heavily used MATLAB and he has like what he has done is through MATLAB he has validated like all these concepts. Many of them they have to be shown, they have to be seen, right? Control everything. So all that he had to be simulated. So for that, Sir has used MATLAB. So you will also have to use MATLAB for those cases. Although MATLAB will not come in the exam as such, the concepts which you have studied or which you have learned will get verified through MATLAB. Okay. Okay, so let me like this is what a small file I have made in MATLAB. Okay, this I have used so that I can run the boost converter model. Like my work is primarily based on the boost derived topology, so I am firmly hoping to focus a lot on the boost converter in this course. Okay, so this is a there are two boost underscore parameter dot m. This is the MATLAB script file and boost underscore converter dot slx. This is the SIMULINK file. Okay, I think SIMULINK takes a lot of time to open. This laptop is a bit slow. Okay, till then I will explain this .m file. So this .m file is used to pass the parameters. Okay, various parameters of the inductance, capacitance, what is the load resistance, what is the input voltage, okay, what is the output voltage I want. Okay, all these things I have passed over here. Just 1 minute. Okay, this is coming. Okay, let me first go through it slowly. This is the duty which I need. This is the on resistance of the switch, the DCR of the inductor, capacitor. All these we will see later. Okay, the non-idealities which are there. Then this is the switching frequency, 100 kilohertz. This E3 means 100 into 10 to power 3. Okay, let us say this is 10. Okay, this is 10. But what if I do 10 into 1 E2? That would actually be 1000. So 10 into 100, 10 to power 2. That is how it is then MATLAB. Okay. So just to clear any confusion, okay, it is not that E 2.718, it is not that one. Okay. Get that, I think you have to do EXP1. That is this 2.718. That is for E. Similarly, the time is 1 upon the switching frequency, 1 upon FSW. Okay. And T underscore sim, this actually is my simulation time. This is simulation time. Okay, so these are various parameters are there. This is my switching frequency. This is my time period, etc. V is my input voltage. Okay. This is the desired output voltage. This is the duty ratio. All that. Okay. These are certain things which are I have defined in the script file. Next, there are certain initial conditions. So my initial inductor current, this is my initial inductor current. This is 0. Similarly, my initial output capacitor voltage. This also is 0. No, not 0. This is Vref minus 1. Okay. Next, I have given a command. This command, it will open the file. It will open this boost underscore converter.slx file. And this command will simulate the file. Okay, all these it will do. Okay, so what I will do is, I will run this file. I will run it. So to run, I must click this. I will run this. Okay, let me run it. And what will happen, this Simulink file will start running. Okay, I didn't need to go and press this run. I just had to click that .m file and I have given the command that you must run it. It will run it. Okay, this makes life fast. Okay, these plots have come. We will look into it later. Now this is my .slx file, my Simulink file where I've made the model of the boost converter. Okay, so if you will see, sorry. So this is where my inductor dynamics I have put. This is my 1/s, which is there for converting my DIL by dt to IL. Okay, this is this 1/s part. This is due to DCR of the inductor, etc. So this is for the inductor dynamics. Similarly, this for the capacitor dynamics, where either inductor current is coming or zero current is coming, and then the load current is being subtracted. Then you divide it by the C out. Then you get dVc by dt. You integrate it, you get Vc. Then you add the factor due to the ESR of the capacitor. Okay. All these things are there. Sorry. Okay. Next is you have to generate a switch node voltage. That depending on the on resistance, when the inductor current comes, or depending on the output voltage, this switch node voltage also is generated. So this is effectively the mathematical model of my boost converter. Now what do I do is, okay, this is my output voltage. I do 1/R, I get the load current. I feed that load current back here. So these things are known as go to and from blocks. That means this IL is connected over here as well as it is connected over here. The reason I use this is it makes it neat. It is not like I put one wire from here to here, one wire flowing from here to here. It becomes clumsy. So to make it neat, elegant, we use these go to and from blocks I used. Okay. So I'm seeing my inductor current, my output voltage, and my Q is my gate signal. Okay. This gate signal I'm generating using a pulse generator. In this pulse generator, I have given my amplitude. I have given the time period. I have given the pulse width, that is the duty into 100 pulse width. I have given the delay is not required in this case. That gate signal has to go over here as well, has to be plotted over here as well. Okay. And this is the scope which will show my result. Which will show the result. Let it open. So this is my scope. Okay. So this is the inductor current, and this is the behavior of the output voltage. Actually, the output voltage has not settled till now, but it will settle if we increase the simulation time. Okay. Now, if you see this, it will not look neat in your reports and in your, some of you are students, some of you are PhD scholars. You will have to make reports, you'll have to give presentations, all this. You can't, directly just take one snipping tool, snip this and put like this and show. It doesn't look good. It won't look good. You can't do that, right? So what do we do is we take these data, use a mux. So it makes this data into a vector of data, and then I take it to my workspace. So I give it some name. I've given it a name boost underscore data, infinite number of data. I made it as a structure with time. Okay. These are changes I have to do. And then what happens is when I run this simulation, all this data which is there, it is taken through this, it is transferred to the workspace. Now, what is the workspace? So this part is known as your workspace, where all your variables, all that data is stored over here. It is stored in this workspace. Let us say your output capacitor, your duty, your switching frequency, all that is stored over here. Okay. So now that data has come into the workspace. It has come in this answer thing. Okay, if you click this answer, it will open that variable and it is a written simulation output. And this is the boost underscore data is what is given. Now we will open boost underscore data. There's option of time and there's option of signals. So this is the time where it gives the time instance 0, 1.67 into 10 to the power minus 11. Very, very small durations it has to save. It has saved that. Similarly, signals are there and signals values are there. This is my IL, my V out, and my Q. All these are given over here. So this is IL, V output, Q. So now I want to access these data. So what I do is I have written in my code extracting that data. So time data is given by, what is time data given by? It is given by answer.boost underscore data dot time. This is my time data. Similarly, the data of all these signals is given by answer.boost underscore data and it's dot signals dot values, which I'm taking over here. So this is my x underscore data. This is answer.boost underscore data dot signal dot values. So I've got this data. Now the first column of x data is my inductor current. So that's why I extract this colon over here. This means all the rows. And this one means the first column. Similarly over here, it means all the rows and the second column, which is my output data. Similarly over here, all the rows and the third column, which is my Q gate signal data. Okay, so I have extracted the data. Okay, from the workspace, I have taken it into certain variables. Now, I will plot those variables. One thing is the data is in very small time, okay? So I want to convert it into milliseconds. I don't want to plot it in seconds. So that is why I multiply it by 1000. Why I multiply it by 1000? In the figure, I t-plot. So this is my x-axis. This is my y-axis. And I'm using red color. And the line width is 2. It makes it more thick. Okay. So this is what I've used. Hold on is so that I can do multiple plots and grid on. And this is my X label. Okay, so this is how it comes up. Let me bring this lower. Sorry. Okay, this is a X label, time millisecond. Y label is inductor current. That comes over here. So if you will see this, this is my X label, time milliseconds. This is my Y label, that is IL and ampere. And this is the inductor current waveform. This is how the waveform will look like. So we have plotted it over here. Similarly, the output voltage also shown over here. Okay. This is what is there. So this has been used extensively by Sir, this method. Okay. This method we have found it to be very useful, and you can also use that, right? And you can go. So all these things are there which you can access. So any questions in this? Any doubts? I know many of you will be tired. It's a very long session. Any questions, doubts? Okay, clear. Okay. So there are no doubts. I can stop sharing. Okay. Yeah. It's very good. I hope it's useful. If you want any suggestions, if you want me to spend more time on explaining sums or explaining concepts, you can let me know. Okay. And yeah, it will be possible to view offline. Offline, it will be soon uploaded on YouTube. Then I think you can download it. I'm not sure. I think that option should be there for you to be able to download it. But it will take time. Tomorrow morning or afternoon, by the time it will be uploaded. Okay. Okay, and MATLAB is a very crucial part because this is not like a theory subject where you have to do lots of derivations and sums and everything. This is more, application specific. So you have to simulate it and then you'll be able to see it. Okay, you'll be able to visualize and understand. Okay. Okay, so if there are no doubts, I'll end this session. Okay, thank you all for joining. Yeah. Okay. Okay, thank you. Please join again next week. Next week again, 6 to 8 on Tuesday. And Teja has his class from 6 to 8 on Monday. Okay. Okay. Thank you for joining. Good night.